Now typically when I know that there's a mess up somewhere, for me, it is often easier to start from scratch than it is to find the mistake. But it depends on time and your faith in finding the mistake.
If we have a negative in the numerator and a negative in the denominator, why is it? Isn't the?
You are correct. Because there's the negative there and the negative there. So that becomes 232 over 107. Okay. Yeah. Also, I'm doing this in fractions just because I typically don't have a calculator on me when I'm doing these problems on the board. If you like decimals, go to the decimal. And apparently, what I just said was so controversial, I've offended Luis.
I'm gonna walk out the room and slam the door. Definitely.
I'm sorry you feel that way.
Bye, everybody.
Good luck. I can't believe you slammed it like that.
Bye.
All right, now that Luis is gone, the answer to the first question on the next test. Don't record it. Well, speaking of which, I know he was in a hurry. Hopefully, I will remember to email him. When do you want the next test? We probably should have some master sets in there. So if we said master sets 20, master sets 21, test 1B. Is that too much crammed together? Okay, what do you propose?
Test 1B following week, so that master set 20 and master set 21 can be
In 2 different
like a week
weeks.
apart.
Yeah.
All right, so that would put 26. So put March 5th. So test 1B on the 5th. Are you good with master set do Tuesday and Tuesday?
Right?
Mhm.
We're making some
Yeah.
decisions.
All right, so we can blame the Lord now.
Is all I thought.
What chapters are the test 1B on?
What?
What chapters are test 1B?
Test 1B is 20 and 21.
Okay.
Sorry.
Dr. Fox, your head is in my way.
That is my life. Any questions right now on 20 or 21? So, yeah, moving that test 1B allows us to get 2 labs in, which actually get good results, which is sometimes a nice change of pace. All right, so up to this point, we've only had one physics equation. The rest is just math and definitions, but basically we had Coulomb's law, and then we expanded from there. So let us now talk a little bit about magnetism. Chapter 22. You with us, Ryan?
Yes.
What do you know about magnets or magnetism?
Like in general?
Yeah.
Well, they create poles, so the opposites attract and like repels.
All right, so magnets have poles, and opposite poles attract, like poles repel. What else do you know? Well, what else do you know? Sorry, I think I put that emphasis on the wrong word there.
There are magnetic fields.
The backwards capital E is shorthand for there exist. So apparently I'm talking to you more. What else do you know? Other people can play. I'm willing to bet she doesn't mind sharing.
I really don't.
How about what are the poles called?
Where is that?
Yeah. All right, let's just start with this. So I have poles, there's a North Pole and a South Pole, magnetic pole. No, I'll wait till the really confusing thing in a moment. So if I have a magnet, I got a North Pole and a South Pole. They do create magnetic fields. So I have a magnetic field that's coming along here, out, and around. So the magnetic field lines external to the magnet go out of north and into the south. And so you'll have multiple field lines here. And just like with electric fields, you typically draw the higher the concentration of lines that are together, the stronger the magnetic field. So I'm gonna have a stronger magnetic field here than I will here. Now notice that the North Pole and the South Pole sort of go together. Wherever I have a North Pole, I've got a South Pole. It's known as a magnetic dipole. unlike electric fields, I can have an electric field, if I took a closed surface, I can have an electric field going out, I can have, in other words, I can have a flux not zero, the electric flux. But if I took any three-dimensional surface here, whatever flows in flows out, no matter where I put it. If I put it here, I still have whatever flows in flows out. So, whereas I have the electric flux through a closed surface is equal to the total charge divided by epsilon sub 9. Total charge enclosed. The magnetic flux through a closed surface is 0. I assume we talked about Maxwell's equations briefly. Looking for some nod of recognition. No nods of recognition. Brian, you're thinking I did not?
I don't recall.
Let's talk about Maxwell's equations briefly. There are a set of 4 equations that are referred to at this point as Maxwell's equations. Now, Maxwell did not call them Maxwell's equations. That was later, sort of honoring him. But the first of Maxwell's equations is if I take the flux through any closed surface, start out with the electric flux, through any closed surface, that's going to be equal to the enclosed charge divided by epsilon sub 9. This is the first of Maxwell's equations. They're sort of in order. It's usually the first one that's taught. This is really Gauss's law of electricity. Or Gauss with just the apostrophe or apostrophe s, depending upon your mood. Gauss's law of electricity. We now hand waved it through it, but there's Gauss's law of magnetism. Which basically says if I add up the magnetic flux through any closed surface, it's going to be equal to 0. So this notation right here, on the other board I wrote it as, I took the symbol for electric flux and then I put a CS for a closed surface. This summation sign means I'm adding up all those dot products. The circle means I'm dealing with a closed surface. If you've had calculus, this would be written as the integral with the circle there, but E dot dA is equal to the enclosed charge over epsilon sub 9. So along the lines of, does that make any sense? So, the electric field, E with a vector symbol over it, sure, I can deal with that. Magnetic field, a B, with a line over it, with a vector symbol over it. Why? Well, the person who started it needed variables. The first one he needed, he used A. The second one he needed, he used B. And it sort of stuck. So, magnetic field. The magnetic flux phi sub B is just B dot A. No, there I used B, okay. I sometimes, for magnetic flux, I will do the capital phi, because it's a flux, subscript N. I think I typically use B, but sometimes I'll slip an M in there. catch up in writing, and then I'm gonna throw one of two confusing things at you. All right, here's the potential confusion. Typically, at junior level physics and below, B is used for magnetic field. Not a problem. As you get higher up in physics, they stop using B for magnetic field without changing the definition of what B is sometimes referred to as not the magnetic flux, but the magnetic flux density. And H is the magnetic field. I have no idea why they do that. But even the people who write the textbooks at the lower levels use B, and then go to the higher textbooks and use H. But I will use B. I bring this up only in case you run across someone or some source that is using H instead of B. They are related to each other. They are separated by a constant, but it is what it is. Okay. Oh, units. So if we look at electric flux, which is E dot A, what would the units of electric flux would be the units of E times the units of A. So what are the units of electric flux?
Newton meters squared per coulomb.
All right, they're happy with this. This is the way that it seems to work in SI units. Magnetic flux would be the units of the magnetic field times the units of area. We'll stick with SI. Well, the units of area would be
Meters squared.
the units of magnetic field. Anyone happen to know? SI units of magnetic field. Okay. It looked like, Laura, you were about to come up with the answer.
We were watching a video about it, but I can't remember.
The Tesla. Actually, as a unit, it should be a lowercase t. And the symbol for a Tesla is the capital T. Named after
Tesla.
all I can think of at the moment, the two units in this course that are not explicitly, they're named for someone, but it's not exactly their name, or the farad and the volt. I think all the other units are named for someone specifically. I mean, they actually use the full name. So this would be a Tesla meter squared. But for some reason, That's too much. That is a Weber. In terms of, there's a more common unit used for magnetic field. Tesla is the SI unit. The other unit that might see, it's not officially the international standard, it's the Gauss. Which has the abbreviation of GA. It's supposed to be a G. Apparently writing on it from an angle doesn't help. To give you some sense of the size of these things, the Earth's magnetic field typically is about a half Gauss. So, as is usual, they sort of establish a unit based upon what's easily found. Although it does fluctuate throughout the Earth, they probably didn't think that at the time. Whereas a Tesla, superconducting magnets are running about 30 Tesla. That's about at the upper limit of what we have. Lab magnets, at least I wrote down lab magnet, 2.5 Tesla. The stuff that we have will be well under a Tesla. It'll be well over a Gauss. The relationship is that 10 to the 4th Gauss